Okay, so it's a pleasure to be here. It's very nice to have been part of this program, and so I'm particularly happy to be part of this celebration of Nicola. I was a little bit shocked when I heard you had your birthday, because for me you look, I would have believed another digit, I think. But anyway, so all best wishes to you and for this birthday. In Japan, this birthday is a very important birthday. It's considered the first half of the life. It has a special name. You're supposed to wear a special dress, and so it's called Kanreki. And so congratulations for your Kanreki. So I want to tell you. So first of all, what I'm going to tell you is joint work with Juliette Bours, who's a student of mine, and Juliette is finishing her PhD at Paris 6, as a matter of fact, and she's starting a postdoc next year in Canada at Alberta. And Guillemette Chapuisat was assistant professor at Aix-Marseille. So joint work we have done together, and everything what I'm going to tell you about today is this. So let me just tell you what I mean by non-homogeneous media. So to start with, let me tell you about what is the classical homogeneous reaction-diffusion equation. So the classical homogeneous reaction-diffusion equation is this equation where you think of U as a density, the density, for instance, of some biological species. And the equation is du dt minus Laplace of u. There could be a coefficient here, diffusion coefficient. So minus Laplace of u is equal to f of u. And this is, so the homogeneous equation is an equation which doesn't depend on t and x. Also, it's important, it's set in all of Rn. And t is time. So this type of equation arises in a number of situations. It's one of maybe the most commonly used, the single most commonly used equation in mathematical biology, as a matter of fact. But of course, then depending on the type of situations you are interested in, the f of u can be of different kinds. And the most classical equations, there are three main types. That's in biology. There is another type in combustion theory, but in biology there is two main types. One is when f of u is of Fischer-Kolmogorov-Petrovsky-Piskunov type, FKPP. So the archetype of this is u times 1 minus u. And so in this case, this is the logistic growth. So for Fischer, KPP. Again, KPP stands for Kolmogorov-Petrovsky-Piskunov. And in this case, the logistic growth rate, you have f of u. What characterizes it is that f of u over u, which is the growth rate, per capita growth rate, this is a decreasing function of the density. So it starts by being maximum when there is no one, and as soon as there is an individual, it grows. But then there are other situations where you want to, where this type of model is not appropriate. And in fact, there are situations where you want to understand what's happening when this per capita rate of growth is non-increasing, is not necessarily non-increasing, but rather can have different regions. So this is called usually the weak-Allais effect. So the weak-Allais effect, from the name of an ecologist, Allais, and the weak-Allais effect is when f of u over u, instead of being decreasing all the way, starts by being decreasing, for instance, and then by being increasing and then decreasing. And the strong Allais effect is actually what you have when f of u changes sign. So this usually, the strong Allais effect is what we call a bistable case, and it's really related to the fact that initially, so for very low densities of the population, the medium is actually has an adverse effect on the population. So instead of helping it to grow, if the population, it actually destroys it. If the population level drops below a certain threshold value, then the population has a tendency there where this happens has a tendency to decrease and to be extinguished. Okay, So this, and there are many reasons in ecology to consider this, and biology also, many reasons. For instance, if you think of a population in ecology, if you think of a population that has sexual reproduction, then you need to have enough random encounters between the individuals of this population for the reproduction to achieve a significant rate. If you don't have enough of these random encounters, then the population, then the mortality offsets the birth rate. So this is a reason to look at that effect. But there are many other reasons. A lot of mechanisms in biology are subject to a certain threshold. So where the growth doesn't happen unless you have reached this threshold. So again, so let me rephrase it. So the Allais effect is related to the fact that the per capita growth rate f of n over n is smaller when the density is near zero. So this is the weak Allais effect, or is actually negative. That's what I'm going to be interested in. And this is just a small, very quick justification of why we use a bistable. But of course, all of you know the bistable equation is a very useful equation to look at. But it's very natural in terms of ecology. Okay. There are many contexts, but it's not only sexual reproduction, but also when there's not enough. For instance, trees can be subject to Allais effect. If the trees are just isolated from other trees, very far away from other trees, there is not enough genetic pooling, and the trees can degenerate, and this may have an adverse effect on the population. So there are many different ways in this can come on. Okay, so here is bistable nonlinearity. So I'm going to be interested in solutions which are between 0 and 1. F is negative from 0 to some value theta, I'm calling it theta here, and is positive after that. So theta will always be in between, and this is what I'm going to use in nonlinearity I'm going to consider here. Okay, so in homogeneous situation, one of the very commonly used, one of the important element there, which is very important for dynamics, which is important also because it's observed in many of the models one is interested in, are traveling wave solutions. So solutions of the evolution equation, which is of the form phi, a function of one variable, say of one coordinate of x minus ct. So here E is a unit vector, and I'm taking E as a direction of propagation. Okay, and c is a constant speed, phi is a profile, so this is called a planar traveling wave because the level sets of these functions are parallel planes which travel with a constant speed, parallel to each other. And if you want to solve this, you just let to the ordinary differential equation, a very classical one that Fisher, KPP, and others have analyzed from the beginning. So minus phi double prime and c phi prime equals f of phi. If you are interested in the front, you want to look at the solution that goes from 1 to 0. So at minus infinity it's 1, plus infinity it's 0. And so in this case, if C is positive, this means that you have an invasion of the state 0 by the state 1. The state 1 invades in this traveling wave fashion. So C is the asymptotic speed. So C is the speed of propagation. I'm going to say something about asymptotic speed of propagation in a minute. E is the direction, and C is positive if, as you know, integral of f is positive. That's very easy to look at. And this is again the invasion of 0 by 1. Okay, so in particular, there are many results for this in the bistable case, in the homogeneous bistable case. I think the first existence and uniqueness result of phi and c date to Fife, the very classical work of Fife-MacLeod. And so this is a homogeneous case. Now, if you want to look at non-homogeneous situations, and there are, of course, a lot of works that address this question. If you want to look at non-homogeneous equation, there are many ways a non-homogeneity can come in. To start with, of course, if you look at an equation where the coefficients of the equation, the nonlinear term of the equation, vary with time and space, so they have a t dependence and x dependence, then you have a non-homogeneous equation. Okay, so it's a very general homogeneous equation. But what I want to say is, and this is what I'm going to look at today, what the non-homogeneity also can come in simply because of the domain you are looking at, you are considering. So in particular, if we look at the equation, the classical, reaction diffusion equation, ut minus Laplace of u equals f of u in a domain omega with some boundary conditions on d omega. So we're going to look at Neumann boundary conditions here. So think of Neumann boundary condition. Then you see, if you're looking at propagation in a domain of this kind, you see that traveling waves do not exist anymore. I mean, or at least they do not. What I wrote down doesn't make sense. You don't have solutions of the form, see here, phi of x1 minus ct. So you need to extend this notion of traveling wave. And of course, then there is this question of what is the speed of propagation and how and so on. But so what I want to stress here is that the mere fact of considering a domain different from Rn, unless it's a straight cylinder, brings in the question of non-homogeneity of the equation. And this is what I want to discuss today. So we're going to look at this equation with Neumann boundary conditions, d nu u equals 0 on d omega. And the type of domains I want to consider are exactly domains of this kind. I want to look at the propagation. I will always look at propagation from left to right. Okay, you always have in mind from left to right, and I want to understand how wave can propagate, what is its speed, and what does it do in a situation like that. I want to compare this situation, maybe some others as well. So before I go on, I want to tell you about the motivation for this work.
What was the graph represented?
Sorry, which one?
Yeah, the graphs, what are they representing?
These graphs, okay. So what I'm saying, these are domains, examples of domains omega, okay? So I'm assuming that I'm interested in the propagation of a species or biological element that goes like that propagates in a domain like that opens or closes down. I want to understand under which conditions they propagate and don't propagate. And what I'm saying is that as soon as you have a Neumann boundary condition here, even though you look at the classical homogeneous or reaction diffusion equation, you are outside the framework of homogeneous equations because of the geometry. And what I'm interested in today, I want to tell you a little bit about the effect of geometry. This is what I want to tell you about. Yeah.
Symmetry of the domain play a role?
No, so I just put examples here, but yeah, it's for some reason it's always easier to draw them symmetrically, but there's no, I don't assume symmetry, no, I won't assume symmetry. I know it's, you may think of this, but those are good examples to have in mind anyways for what I'm going to tell you. So let me tell you about the motivation for this. For looking at this. So the motivation is actually a model comes from neurosciences, and it's a question that comes from the spread of cortical spreading depressions in the brain. So what is a cortical spreading depression? So this is depolarization of the neurons in the brain that spreads, that's quite large, and it's a transient state, but it spreads like a wave, slow wave. It's of the order of millimeter per minute, millimeters per minute, and it's a depolarization of the membrane of neurons. Normally, neurons are in polarized state, and this is a depolarized state, and this is related to pathology, which is related itself to ionic exchanges between the interior and the exterior of the cellular space. So those are CSDs, and they seem to be related. I mean, people have wondered for a long time whether they happen. Apparently, this is one of the ideas that CSDs are strongly related to the migraines, in particular the migraines with auras. Auras are when you have migraine is so strong that there is an hallucination. Many people are actually subject to this, migraines with aura. It's also related to strokes, or people think that there might even be an element related to this in epileptic crisis. So one of the things, one of the elements here that triggers this research is that this has been very well observed, this cortical spreading depressions in brains of rodents and mice and rats. And not only that, but there are ways to stop those. People know how to stop those, and this has seemed to be efficient. So one really wonders whether there is something like that in humans or not. And so far, and the CSDs have not been observed in humans. And the possibility of CSDs is a question. The question is why you observe them in rodents and why not observed in humans. So let me tell you about the modeling, and I will interpret the results I'm going to tell you about as I go along. I'll tell you about the mathematical results and their significance for this model. Suffice it just to say that this is a starting question. So the modeling is really this. You assume that you have this density, say U, which has two states. The stable state 0 is two stable states. So one is a normal polarized state, which is going to be represented by 0, and the completely depolarized state is when the density is 1. It's completely depolarized. And what is known also about this is that there is really a threshold for passage from one state to another. In other words, normally if you make a small disturbance, it will come back to its original state. So there is a threshold on the ionic disturbances for passage from 0 to 1, from the normal state to the depolarized state. And we are going to here, this model I'm going to tell you about is only focuses on the depolarization stage. And so it's a transient, but it lasts several minutes. It's a transient state. And now, what is also another important element is that this depolarization, the brain is constituted of two main components, which is the gray matter and the white matter. And this depolarization takes place in the gray matter. And what is usually considered is that you have a kind of absorption or diffusion in the white matter, which surrounds it. So this is the situation. You have depolarization in the gray matter. Now, it turns out that brains of humans are very different from brains of rodents, even though Luis told me that brains of humans have DNA, at least DNA is very, very close to that of the fly, right? Yeah, very, very close to that of the fly. Nevertheless, the brain comes out with quite a different shape, and this is the brain of a human. And you see, so there are many differences, of course, and one is that it's much more contortuous here, but also I don't know if you can see from here, but this is the gray matter is superficial in the human brain. It's very contorted, it's superficial. Inside is white matter, whereas the rodent is essentially gray matter. And it's rather homogeneous. And has a sort of constant thickness. Whereas here, if you can look at it a little bit closely, you would see that there are big variations in the thickness. So it goes through very narrow regions, like here, and then opens up again to big regions, narrows down here, opens, very wide, thick, and so on. So there are many variations of which. And the question we want to understand is, can this difference in geometry account for blocking and propagation, which is the theme of what I want to tell you. So the model has been constructed. There are many models of this kind, actually. But the precise mathematical model really was done in a series of works of Emmanuel Grenier, and Chapuzat. So the first work of Chapuzat in her thesis, actually, was about constructing this. This was done in collaboration with some people in hospitals. And so basically what they end up is having a reaction-diffusion equation of bistable state, which occurs only in the gray matter, And the bistable is really related to what I was telling you about this threshold mechanism, okay? And there is really absorption in the white matter. Guillemette has done some work on this, on numerical simulations. But here we're going to use Neumann boundary conditions rather than imposing an absorption. I don't think it would change very much, but anyways, we're looking at Neumann boundary conditions. And again, so our goal here is to understand whether the variations of the thickness, or the variation of the gray matter thickness, has an influence or not on the propagation of CSTs. Okay, so this is a mathematical problem I'm going to look at. So the framework we're going to use here is so it's what I told you at the beginning. So the most classical reaction-diffusion equation, dtu minus Laplace u equals f of u, where f is bistable. But now we are looking at this think of omega as a domain with varying cross-section. So think of a domain with varying cross-section. This is our omega, and omega so is a set of x1, y, where y is in some open set which varies with x1. So it's an infinite cylinder in the x1 direction with varying cross-section omega of x1. Now, f is going to be a bistable function. I'm going to assume that the integral, and more precisely, the integral of s to 1 of f of s ds is positive for all s in the closed interval 0, open in 1. And also, I'm going to look at the situation where the set itself, omega, is a straight cylinder at minus infinity. So omega converges to a straight cylinder as x1 goes to minus infinity. And the questions I want to address are this. First question is, can we describe waves coming from minus infinity? So since there are no traveling waves here, can we nevertheless describe what we mean by a traveling wave or generalized traveling wave here coming from minus infinity? So again, we have like a straight cylinder at minus infinity. Can we describe a wave? So that's the first question, coming from minus infinity. Then the next question I want to discuss is, does this wave propagate, or is it blocked is as a geometry? And the question is, indeed, the third question is, can you describe what is the effect of the geometry? How does it depend on the geometry of the domain? So the example of domains I want to have in mind, remember this is the human brain, right? So the examples of domains I want to have in mind is, I want to look at the propagation into the direction of a narrowing cylinder. So again, I'm always looking from left to right. So this is narrowing cylinder. And here, so again from left to right is propagation to widening cylinder. And so I'm interested in abrupt transitions or more progressive gradual transitions here. Okay.
What does it represent? I mean, if you look at the brain, is it a cross section through the gray?
So it's really a simplification, right? I'm not looking at this geometry exactly. So I'm looking at the geometry which you can think is indeed would be something like that, right? You think of this as maybe 2 dimensions simply, and just you want to understand the effect of it. But of course, the geometry of the brain is more complicated than what I'm saying is. So I'm just looking in 2 dimensions, or in 3 dimensions. Actually, dimensions will be true in any dimensions. But I'm just looking at this effect of going through. Of course, in the actual geometry of the brain, it's more like a 3D set, of which the thickness at some points is small and so on. So it's a little bit different, but nevertheless, I think the phenomenon is captured by this geometry, right? So it's not the geometry exactly, but we're going to look at exactly what's the effect of thickness here. Okay. And it's an unbounded domain, so the brain is not unbounded. But okay. So let me tell you then about the first question I mentioned, which is what is a generalized wave? And indeed, so we are looking at the situation of a smooth function f, which is a bistable, such that the integral of f is positive, as I said before. Then there exists a unique planar traveling wave, phi and c. So the planar wave in all of space, which only depends on one variable. So phi is given by an ODE. There is a unique speed, which is positive, the unique speed of planar traveling waves, c, here. And so there is a unique couple, if you want, phi c, with c positive. And I'm also assuming that omega is say, a straight cylinder when x1 is close to minus infinity. Then the result is this. So under this hypothesis, there exists an entire solution of this problem. So by entire I mean defined for all times. An entire solution of the problem of this problem, the tu minus Laplace u equals f of u in this cylinder omega for all times. For all times, that's the main thing. That's already a very strong property, and satisfies this boundary condition. And why do I say that it's a generalized traveling front? Because of this. Because we can construct such a solution such that if you look at the difference between this solution u at time t in space x minus the traveling front solution, planar traveling front solution, phi of x1 minus ct, then this difference goes uniformly to 0 when t goes to minus infinity in omega bar. So if you look very far backwards in time, what you see is you see exactly this planar traveling front phi, which is coming very far to the left. So this is what is here, right? And in addition, so that's strong property. In fact, this condition that u looks like this traveling wave at a very negative time defines u uniquely. There is only one solution u which is defined for all times, which is globally defined, which has a kind of initial condition at minus infinity, which is of this kind. So this is what we call a generalized traveling wave. It's a very natural object to study. It's well defined. It's unique. And it exists. So we call it generalized traveling wave, transition front. In addition, we can prove that this traveling wave is always between 0 and 1 for all times or space, and it's increasing in time, and therefore has a limit. It converges to a certain stationary function, u infinity of x, which is a positive, strictly positive function everywhere, and this is a stationary solution of therefore of the elliptic equation with a Neumann boundary condition. So as I say, so this is what we like to call them. I'm sorry?
The stable equation, the elliptic equation.
Yes.
In which domain?
In omega, in all of omega. Everything happens in omega. Omega is fixed. So you have
omega is a domain in Tx. And
yeah. No. So omega is a domain in X only. It doesn't depend on T. No. Okay. And so it's a cylinder, and I have an equation which is defined in T and X, but X is always in omega, which is fixed. Okay. Yeah.
Yeah, I can relate. The omega set is this omega that you show is a channel that is either enlarging or
right.
So the important condition is that at infinite it becomes cylinder.
Right. It can be anything. As a matter of fact, it can be
cylinder in the sense it could be varying cross section.
In general, it's varying cross section. What I'm assuming here is that near minus infinity, it's a cylinder, straight cylinder, right? So the only assumption I make here is that if you look very far back, you have a straight cylinder. But this, after I'm not making any assumptions really, it could be even bounded on the right-hand side, or it can be, think of this following situation, which is, that's actually an interesting thing. We were wondering for a while, what is the notion of traveling waves in bent cylinders? So you have a domain, which is cylinder at minus infinity, but then it goes like that.
Yeah.
So what this theorem I'm quoting here gives you what is the generalization of traveling front for something like that. So there is a solution which is defined in all times. Presumably, we want to understand whether it's going to propagate all the way here. And we know that there is only one which comes from phi, right? And of course, you can look at translations of phi. You have other ones which are translations in time of the u.
But the speed of the traveling wave that you get there depends on how the domain is varying.
So this is what I want to look at, okay? So for the moment, but in general, there is no such a thing as a globally defined speed. There is no such a thing because, if you think of this, think of this situation, right? I mean,
right.
You don't have a speed. It's another object. But the only thing you can say is that here, when the entering wave, it enters as a planar traveling front. And what I'm saying in this theorem is that it's enough to impose this to get a unique solution which starts like that. So it's almost like you can solve the Cauchy problem for this equation by imposing that it is at minus infinity a planar traveling front with a unique speed c given by the planar traveling front. But then knowing what it does after is what's gone. But what I'm saying is that this construction gives you exactly this notion of generalized traveling fronts. And we want to understand, so this is what I like to call it a transition wave from phi of x1 minus ct to u infinity. And the properties of u infinity will indeed will characterize propagation or blocking, or we'll discuss, you'll see, we will discuss also the fact that it can be incomplete propagation or complete invasion, depending, all this will depend on geometry of omega.
Is this assumption of the cylinder compatible with the traveling wave compatible with Neumann data?
Yes, because you see, if it's, think of this as a cylinder, right? So it's really, but I mean cylinder here, I mean straight cylinder. So if you have a straight cylinder, you have Neumann data. So it means that you look at minus infinity, you have a straight cylinder, and if you have something which depends only on this coordinate, it has Neumann data here. So indeed, that's why what I'm saying here is for Neumann data. It would be a different game if I had, you know, again, you can look at, that's something we should do, I think. We can look at, if we think of the brain again, this should be an absorption, should be defined everywhere just with an absorption, and we can look also at propagation in this kind of situation. But the way it's defined is that indeed at minus infinity, this is, so asymptotically it is in this direction, is one direction in which asymptotically it is like the equation for planar traveling fronts. Okay? Okay, so I'll call complete invasion will mean when u infinity is 1. So let's look at, so now we have, so that's the first question I wanted to address. How do we do this? And I should say, by the way, that this result here is really built upon earlier work I did with Amel and Matano. In CPAM, which appeared in CPAM in 2009, where we were interested in bistable equation, how there is a front passing an obstacle, a bounded obstacle, and the method we introduced there actually works for this general situation. Okay, so now we have this first element, and we want to understand now what's the effect of geometry. So let's first look at propagation in the direction of a narrowing cylinder. So we go look at propagation from left to right, and we have a cylinder which becomes narrower and narrower. What do we mean by this? We simply mean that the outward normal derivative has always first component which is greater than or equal to 0. Okay, that's what it means. So we assume that omega is a straight cylinder for simplicity. On the left, it can be asymptotically, that wouldn't change. The first normal derivative has always a first component which is non-negative. And we also assume that near plus infinity, it's also a cylinder. So we want to understand how this transition region, what's the role of this transition region. F is as before, it's bistable with a positive wave speed, and phi is as before, and we have this unique wave which we have just constructed. So in this case, there is always complete invasion. So in this case, the wave that I mentioned, u of t and x, will converge everywhere to 1 as t goes to infinity. At every point in the cylinder, it will be 1. Moreover, it will do so with an asymptotic speed of propagation, which is c. So c is the unique speed of planar traveling fronts, right? The unique speed of this ODE. Unique speed of this ODE. And here's the definition of what it means to say that it will converge with the asymptotic speed of propagation c. It means exactly the following. If you are running with a speed gamma in the direction x, if you are running with a speed gamma in the direction x, any speed larger than c will lead you to see only the state 0. If you run ahead of the front. If you run with any speed gamma less than c, and you look backwards, you only see one. So when those two things happen, you say that c is the asymptotic speed of propagation in the x1 direction. So you can prove that in this case, this is what happens. So in some sense, this narrowing cylinder, the effect of a narrowing cylinder is indeed, it shuffles things around a little bit, but basically you arrive with a speed c for minus infinity, and after you have passed this region, you recover the speed c and you continue to invade with speed c. So there's not much, this narrowing thing has not destroyed your wave at least. And let me show you if this works. Let me show you a computation. So the numerical simulations were done by Juliette Bourrouz. They're part of her thesis. And this is what you see. So this is a numerical simulation. It works. So you see, this is a planar traveling wave. It arrives at a situation where it's a little bit wobbled, but nevertheless it passes the passage and continues with the speed, the same speed as before. Okay? Okay. So yes, please.
Isn't it counterintuitive in a sense?
Isn't it counterintuitive? Yeah. Okay. Okay.
No conservation.
Yeah. I will. Those things are a little bit surprising. What I'm going to show you, and I will comment on this later on when I show you a case when it doesn't happen. I will want to comment on this. Okay. But you're right. In some sense, it's a little bit surprising. So the proof of this, I don't think I have time to say much, but the proof of this is simply to observe. That's a very simple observation, but very useful here. And it's not completely obvious to start with, that in this case, this geometric condition is such that the planar traveling wave is simply a sub-solution of this. So you can fit it below. Why is it a sub-solution? It's because phi has only x1 dependence, and the direction of the normal is such that it is a sub-solution. So this is where the geometric assumption comes into role. It's only to say that this is a sub-solution. And if this is a sub-solution, it sort of forces, it lies behind, it travels with speed c, so it forces it to go with, you have below it, you have this planar traveling wave with speed c, and it sort of pushes this to go above with speed c. Of course, then you have to prove that it's not more than c later on, but that's what is happening. And okay, then you need to construct. The super solution is more complicated, but now let me tell you about the opposite situation, which is when you go into widening cylinder. So you propagate into widening cylinder. So the result is this. So you look at a cylinder where there is, which is basically, say, of a cylinder of diameter epsilon, or included in a cylinder of diameter epsilon, and goes into a right cylinder which is fixed. And you want to look at the dependence of epsilon, respect to epsilon. The theorem is this, that if epsilon is small enough, then there will be no propagation. I mean, there is always propagation starting from minus infinity, but the propagation will be blocked. It will be blocked exactly here, that is, it will not be able to invade this right cylinder. And so this is a result, u of t. So how do you formulate it? So remember, u of t in x goes to u infinity of x. And so the fact that there is u infinity, of course, we have a parabolic equation here. So an elliptic equation for u infinity. So u infinity is nowhere identically 0. But what does it mean that it's blocked? It means that u infinity decays to 0 here. So there is a barrier which is so if I look at, say, at dependence on x1 at y equal to 0, for instance, so it means that we have a front which propagates into this, but will converge to this, and this is pinned down. In fact, this happens very close to the origin here. It's pinned down, doesn't let the front propagate further. Okay. Now, I insist on the fact that here what we do is we fix everything. F is fixed, the right-hand side is fixed. It's really epsilon, the width of the left cylinder, which is which becomes small. No, okay, thank you for, because I'm not clear. Here what I'm saying is that, you know, this is, I'm representing is completely different. It's not the geometry of the set, right? This is x1. So we are looking at y equal to 0, and what I'm saying is that I have this wave coming, but there is a fixed u infinity of x1, say. I represent it, in fact, it's u infinity of x1 and y. But there's a fixed one that sits there and doesn't let this thing invade. Okay, so this is what I represent here. So it's not the geometry. Thank you for making me say this more precisely. So this is the function as a function of x1. It's just a representation. You have a fixed stationary solution which sits there and doesn't let the wave propagate. So this is the effect, and you see it's a geometric effect. It's really the fact that you go into opening. Now, let me show you this. So here's a computation simulation of this situation. You see it arrives, and from the left it's like a phi of x1 minus ct. There's no doubt about it. It arrives here, and it doesn't manage to get in the wider cylinder. Now I would like to tell you about this. So why it's a little bit strange, because you may think that it's counterintuitive in some sense. Before we had this situation where we have much less space to invade, and the invasion takes place. And here, all of a sudden, we have a lot of space, and the invasion doesn't take place. So the reason has to do with the threshold effect. It's really a bistable effect. You wouldn't see this in the KPP. KPP, this doesn't happen. KPP, there are lots of things to be done still in KPP to be understood in this framework, but certainly you don't have this type of phenomenon. And think of this. Think of the following, right? Think of for instance, what I described sexual reproduction of animals. So when all of a sudden they get into this wide space, they spread because there is diffusion. They spread, and all of a sudden they never manage to reconstruct enough of a population size from which it will continue to spread. They just spread, they go wild, and they don't, and the equilibrium is such that they don't reproduce there anymore. And this is because this is really related to the fact that you have an abrupt transition. You wouldn't see this in a gradual transition. Whereas if it's narrowing, of course there's less individuals who will pass there in this narrowing band, but they always have a high density enough to reproduce and to create a population. So this is the explanation for this. Okay, so again, so you see, if I just want to formulate this in the words of the motivating situations that I described at the beginning, what you have here is that if you have an abrupt opening, then this will block the CSD, cortical spreading depression, and the depolarized state cannot invade the gray matter if there is a very sharp transition like that. So the idea of this is the following. Basically, what you want to do is you want to look at the domain. What you want to do that is to build this U infinity. Basically, that's what you want to do, is to build this solution. In fact, what we do, we take exactly 1 here. We take a value 1 at some point. So we want not only to do that, but we can, in this, if you think of this as, again, this is a function of x1, right? I represent a graph of function of x1. I want to put 1 here, which is good enough because all our functions sit below 1. I want to construct such a solution. So basically, I want to construct a solution of the stationary equation, Laplace w plus fw equals 0, in the cylinder x1, the part of omega which is x1 bigger than -1, which satisfies the Neumann bounding condition, and which is identically 1 here. And, you know, and goes 0 at r, but then we let r go to infinity. So it's -1 r, but then r will go to infinity. And we can do that, we can construct this solution basically by observing that if you look at the energy here, so the energy is this one, jd of w is the half of gradient w squared plus f of w. F is the integral of s to 1 of little f, right? So the differential of f is minus little f. So it's plus here fw, and if you look at what f is, you can see that if epsilon is small enough, you can prove that this functional has local minimum close to the, among functions which the values is 1 on the left-hand side, and otherwise unrestricted on this, one. Okay, so it's one here. This one here, otherwise unrestricted, and you can look at these functions. If you take a particular function W0, you can show that around it, if your epsilon is small enough, then there is a sphere, say, such that the value at W0 is strictly less than the value on the boundary of this sphere. You can construct this explicitly, and this will tell you that there is a local, of course not going to be W0, but there is a local minimum. And this minimum is exactly what you want. But in addition, the way it depends on R is that this delta can be chosen uniformly with respect to R. So you have not only that, but you have something which is 1, which also remains bounded in H1 norm. Therefore, it has to go to 0 at infinity, and you can prove this because of this relation. So you can prove that W infinity goes to 0. And W infinity is indeed the barrier, as I explained, that serves to block the solution in the big cylinder. Now, so this type of situation, which I've described in one case, in fact is something which happens always when you go through very sharp transitions, provided you exit these sharp transitions. So here are some situations which I've described. So if you go through something, an isthmus, right? You think of a population that goes through an isthmus. If it goes into a sharp region like here at this side, or if it goes here, so you have a situation like that. If this is big enough, or likewise if this is big enough, then all those things, all those situations will lead to blocking of the wave. And you see, coming back to your question, you were asking about the shape of the brain, right? So you may think this is a very caricatural representation, which it is, of course. But what I want to say is that in this case, right, if you think of higher dimension, if you think of 3D, a situation where it's 3D and say it's finite in this extension, then the same result will be true if the thickness gets small only in one direction. It doesn't need to be just a narrow channel. If those things, are independent of the other variable, but only there is a small passage, a small sheet, if you want, then the same result will be true. Now, what turns out, so you may wonder, okay, so is this related to the proportion of how small it is narrow at the beginning to how wide it becomes, or is it something else? In fact, it's something else. It's really absolute result on the size of the left cylinder. That's why I insisted that it's only related to epsilon, the size of the cylinder. It's not a ratio. And this is related to the fact that F is fixed. Otherwise, we could scale everything out, of course. So the result is this: if you have large enough cylinder, straight cylinder, so R cross a ball of radius R0 in Rn minus 1. So if you have a cylinder like this with diameter 2 R0 of the cross section, so if you have a whole cylinder like that, included in all of omega, then the result is this: if there exists a critical R star, such that if R0 is larger than R star, there will always be propagation, perhaps partial, but it will never be blocked. So what do I mean by not blocked? I mean to say that so U goes to U infinity when T goes to infinity, but U infinity will be bounded away from 0, at least in this cylinder, in this inner cylinder. So think of the axis. So if you look on the axis, U infinity of x and 0, so U infinity will be bounded away from there all the way to here. So this means, as opposed to the previous situation, you had something arriving here, and there was a barrier here, so the further you looked away from the barrier, the closer it was to 0 everywhere. Here, there is no, as you may go as far as you want and still see the non-zero situation. As far as you want. It's bounded away from 0. Yeah?
Maybe the scaling is actually that the small part of the channel with this epsilon cross section is going to be a small portion on the bistable points for the bistable instability, right?
Well, I'm sorry?
Yeah, because you have the f of u.
Yeah,
You say it doesn't have to do with the widening of the
yeah.
but it must have to do on the distance on which the values of u become bistable.
Irene, you're absolutely right. It's a very good, very good intuition. This is exactly what is happening. You need it, so let me formulate it the way, but it's really related to this bistable situation. So the way it is related to bistable situation is this. If you look at, say, a ball of radius r0, if you look at the ball of radius r0, and you look at solutions of the Dirichlet problem in this, okay, in this ball. So look at the situation where you have this ball of radius r0. You want to look at u. So you want to find a solution. Let me call it w, which is 0 here, or z. Let me call it z, and satisfies Laplace z equals plus f of z equals to 0 in the r0. And with zero data, and you want to find a positive solution of this. Okay, you want to find a positive solution of this. So the result for this equation, for this situation, is this: if r0 is small enough, there is no positive solution of this, and this is exactly related to the fact that you have bistable. You can prove this, that there is an r0, so that because of the bistable structure, if r0 is small enough, you cannot have a solution. And when r0 becomes large enough, there is enough, and it's exactly what you were saying, there is enough space for the solution to go over a large enough chunk where it's above theta, so that there is. And so there exists a critical r0, there exists a critical r0 star, maybe let's call it, I don't know, so that there exists a solution if there exists a solution if and only if r is greater than or equal to r0 star. This is a variation actually of a result, an old result of Paul Rabinowitz. And actually what we use there is really also related to some old work I had done with Pierre-Louis Lyons, where we were looking for what we called scalar field equations, how to approximate solution of scalar field equation by letting the radius go to infinity. So we had to analyze this and to look at this. The result of Rabinowitz is more complicated than this, and likewise what we use there is a little bit more sophisticated than this. The result is this: there exists an r0 star, so there is a solution if and only if r is greater than or equal to r0 star. Actually, Paul had it by saying when r is large enough. It wasn't exactly this setting. He had the domain omega, and there was a constant here, lambda. Lambda constant had to be large enough for the solution to exist, and small enough, no solution. But there is actually, in this case, there is an exact threshold. And and what Paul proved was that when r equal r0 star, there is at least one solution, no solution before. But when r is strictly greater than r0 star, there are two solutions. There is a pair of solutions. So there is a maximum solution, and there is another one which is a little bit more tricky to find. This you find with an argument relying on topological degree. So it's a very nice result. And this second solution, which is hard to find, is the one we showed with Pierre-Louis Lyons to converge to the, when r goes to infinity, to the ground state solution. Not the maximal goes to theta, to 1, sorry, in this case, goes to 1. And it's exactly related to this bistable structure. Okay, so it's exactly, so in fact, I should say this, and you know, it's exactly in the spirit of what you said. In fact, this R0 can be, in some sense, is explicit. The R0 which is there is the same R0. It's really, you look at when you have a solution for this, when you have a solution of this R0 gives you this thing. And there is another one which you can also, there is another, but let me not fuss about this. Okay. And now, so the question, so here we have partial invasion, so my time is up. Let me just say very briefly, you have partial invasion. Here, what are the conditions to have complete invasion? So this will come as okay. So here is an example. So it's the same situation as before, except that this lower channel is a bit thicker. And you see, so what's going on? This arrives at the opening of the domain, but now it passes, as where before it was blocked. Now, the interpretation, again, I can tell you a word about the interpretation of this. This is really related to the fact that when it arrives here, you see, before entering, this population starts reproducing here. They have to form a kind of base for the invasion. So here they form this base. But what is interesting is that it's large enough for this base to have a significant effect, from which they depart and then they colonize they go to other areas. And this is related, you know, there is this result, a classical result of Five-McLeod or Weinberger, which is in this thing, if you have an initial datum, think of initial datum which is with compact support in the bistable case. If the initial datum is small enough, there will be extinction, if it's on a domain small enough. But if it's big enough, if it's larger than theta plus something on a large enough domain, then it will invade everywhere. So this is related to this. There is, in some sense, here you have the formation of a domain where the initial datum, you take this as initial datum if you want, is large enough so that they converge. So what is the interpretation of this? They arrive, but they all exit at the same level, at the same place. So they exit at the same place, so they congregate there. There is reproduction there, birth, which offsets. And once they have enough, they have created enough population, it continues to increase.
Somehow, it's also related to the models of a slow combustion, right? When you put the ignition function approximation with the bistable ability, you could think of that as being the burning front, that if it is too thin, it doesn't expand, right? But
so certainly it's true that it applies in the same way to combustion models. That's certainly true. I mean, the same reasoning, the same proofs work if you put the combustion nonlinearity with ignition temperature. And so it's not so what plays a role would not be the flame sheet, as it were, but there is enough heat created at a region so that it starts burning the other thing. Whereas if the channel is very small, there is never enough heat created at the exit so that it lights the fire. Okay, so this is exactly that's the analogy. Okay, so if the small portion is large enough, it will always invade. Okay, I think my time is up. Let me just say that gradual invasions always pass. So even if you have this epsilon here, if it's gradual enough, it always passes. And I want just to illustrate this on this picture. This theorem we proved, but that's a good. So here's an example where the passage here from here to here, if it was just this region here, would not pass, would be blocked here. But here we do it progressively, and if you go progressively, they slow down. Of course, it has its difficulty. But nevertheless, it grows, and eventually there's enough of it, it has been formed. And this is representing the theorem I just showed you. Okay. Okay, so... okay, I just want to say can I exceed my time by a few minutes? Let me just say that, so the question of complete invasion is to know under which conditions is it equal to 1, really. So we have several geometrical conditions. It turns out that this is a very interesting problem. Actually, I was really surprised to find it. So here's a result that will show you this complete invasion. So let's assume that there is indeed. So we want to look at situation. We are looking into widening. So let's look at the widening. Remember, for narrowing, we know that it's a complete invasion in the sense that it converges to 1 everywhere. So this we know. So the question is, we know that for widening cylinder, if there's a large enough inner cylinder, it will not go to 0. But when can we say that they're identically 1? So let's assume that we have indeed this large enough inner cylinder all the way, right, inside omega. And let's assume that past a certain point, the domain containing x1 part of the domain which is contained in x1 bigger than L is convex and unbounded. And let's assume that everywhere nu1 is less than or equal to 0. Okay? Sorry, it's greater than or equal to 0. Nu1 is greater than or equal to 0. There's a mistake here. And so you can think of domains like this, right? So this is exactly this domain, and again, we're assuming that it's convex on y. It doesn't need to be convex all the way, but it's convex past a certain point. Then the result is that under these conditions, and this geometric condition on the domain, the invasion will be complete, namely u infinity will be 1. And I don't have time to go into the proof, but it's really a method of sliding balls in a sort of ingenious way, and to get that u is identically 1. And there is another class of domains which I like here, which we like to call star-shaped with respect to the x1 axis. So what does it mean? It means, okay, again, we have this cylinder to the left, we have an inner cylinder with size above critical, omega is bounded in the other directions, and let's assume now that so in dimension 2, if you think dimension 2, let's assume just that nu2 is greater than or equal to 0 at every point of the boundary. Or more generally, nu prime dot y, so if the coordinates is x1, y, nu prime dot y is star-shaped. So the reason why I like to call it star-shaped with respect to the axis is if you had nu dot x greater than or equal to 0, you say that it's star-shaped with x, with respect to x. That's what this condition means. So in this case, you don't do it with one fixed point, but you always take the point on the axis, which has the same coordinate, and you say that it's star-shaped with respect to this point. Okay? So any slice x1 is called constant is star-shaped here. Then the invasion is complete. So this is enough to guarantee invasion. And I just want to say that you cannot hope, you need to have a condition. Those are not technical conditions. The two conditions I mentioned here, those are not technical conditions. You know, if you go away from this star-shaped thing, you may have situation where you're looking at a domain propagation into a domain like this, and if this is thin enough that u will never be complete here, because that's part of the result we proved, as a matter of fact. We can redo the same thing, and there is here something that blocks it. So the propagation, so you need to have some extra assumption, which in particular precludes this. Okay, or you can think of other things, right? You can think of this going and being like that, right? And then opening again. You may have other passage. So it will be complete here, but not complete there. These are the domains I'm drawing. Okay, so I'll stop here. Nicola, happy birthday. And thank you for your patience.
We have maybe one question.
Well, I wanted to understand if you are talking about modeling. I'm not talking about the mathematics, but about the modeling. What would happen, for instance, it would be a more natural thing to take something, let's say a torus, with different weights and different points and so with changing weights, sort of. That would seem to me to be a somewhat nearer model to the real situation. Here, taking something infinite in both directions, it's somewhat artificial, no?
No, but then you have to criticize all the literature that has been produced.
I'm not talking about the literature.
Let me just finish. You have to criticize all the literature that has been done about invasion phenomena using traveling waves. Traveling waves always assume that it's infinite, it's an infinite domain. So if you want to use this type of things to understand invasions, they've been very successful, by the way, at understanding them, then you need to have an infinite domain. And the reason is this, that if you do a bounded domain, then you start having effects of, you start having boundary effects, you start having short distance effects, which you cannot disentangle from the phenomenon you want to look. So the reason why people in ecology, in biology, always use these infinite domains is not because they think that the world is infinite or that an individual is infinite, but because they think that this is a good way to look at just the phenomenon of understanding the speed. And the speed, in these cases, the speed is really something that in some cases has been measured. I mean, it's really so you can even when you take infinite sets. So that would be the short answer. But of course, that doesn't preclude, you know, what you're saying to be done. I mean, if one could look at I'm sure one can look at other situations, but you see, if you look at a torus, right, as you proposed, you want to look at the propagation, right? So what will happen? So we can look at the torus and indeed do this type of things.
Disturbance at some
Okay.
process.
So let me just tell you. So one can look at this, right? So one can look at this situation where you have a torus. I'm not drawing it very well. Okay, an annulus thing, or a torus, may even if you want. Okay. Okay. And you go through a small isthmus here, let's say. Okay. So you may look at something that starts to go there, but the problem, you will never. So what you will do, you know, it will invade through this part. So you will not see the phenomenon you want to look, because so if you take those two things apart, you will see what it means to go from one and go across here. If you want to look at how it goes here, it will just propagate this side. So but nevertheless, I think you know there are some things that can be done also. It doesn't mean.
Look at what happens when t is large but not infinite, maybe.
Sure.
Well, maybe one just can prove that when t goes to infinity, this converges to zero.
Of course. Yeah. Exactly.
It's a matter of scale.
Exactly. Yeah. It's a matter of scale. So the right scale, in some sense, is more captured by this type of things I was showing. But what I meant to say with my answer is that, in fact, this is this sort of assumption where you want to look at this. It's not particular to this model. It's really all the models that look at infinite. You know, there are other criticisms that can be made, and in some sense more relevant is to look is a continuum limit. Here we look at a continuum limits model. Some people are trying to understand what it is when you have, for instance, in ecology, when you're down, in particular when you cross this, you're down at low number of individuals, and then you may want to mix this with a discrete model. So that's another question at this point.
Okay, so I go here again.